So, good evening, ladies and gentlemen, and welcome to the 192nd event of the Chennai International Center. So, we've been meticulously keeping record right from 31st July 2016 when we started. The type of events, the number of events, these various subjects that we have dealt with over a period of almost 8 years. But today's subject is a very different subject, and rightly so, as Professor Rajneesh was just mentioning, that the subject has got tremendous implications both from an overall corporate regulatory standpoint as also how a common man should understand the importance of CO2 and all the terms that follows that expression in the subject, to the extent that he has to be not only aware but he has to also implement some of the issues arising therefrom. We are extremely fortunate to have Mr. Rajneesh Kumar to take us through this subject. And he, as a professor, would have dealt with it in a classroom situation. But he has assured us today that he will deal with it in a manner that all of us can relate to it in the way we should in our day to day functioning. Now, I learned a new term today, sequestration. In fact, I asked him, what does it mean? It is synonymous with the term storage, but I am not going to discuss more about it. That is his subject. But clearly, one takeaway has come already, and many more will is going to follow during the course of the next 45 minutes. So, it is my duty to also introduce the speaker of the day, Rajneesh Kumar, FRCS, is a professor in the Department Chemical Engineering at IIT Madras. Prior to that, he has served as a senior scientist at CSIR NCL and research associate at National Research Council, Canada. His PhD is from the University of British Columbia, Canada, and has research interests in gas hydrates, carbon dioxide capture, process development, and scale up. Work from his research group are all well cited, and so far they have published more than 100 research articles. Please give him a big hand, ladies and gentlemen. He was recognized as the highly cited researcher in the year 2018. Rajneesh Kumar is the most recent awardee of the Shanti Swarup Bhatnagar Prize for his contribution to engineering science. He is also a recipient of NASA Scopus Young Scientist Award in Chemistry for the year 2016. More recently, in 2020, Rajneesh Kumar received Dr. YBG Verma Award for Excellence in Chemical Engineering Teaching at IIT Madras. So, it is our pleasure to welcome Dr. Rajneesh Kumar, and he will take us through this very interesting subject over the next 45 minutes or so. Thank you, sir.
Thank you, sir. It was a pleasure to listen to you and to have met so many new people. So, as I have been kind of reminded that I'll have to explain this word sequestration, I'll certainly try to do that. See, carbon dioxide capture, utilization, and sequestration, basically, the way it is written, it's a three-step process, typically. I'll try to explain what exactly is this in academia. People typically call it CCUS. CCUS basically is carbon dioxide capture, utilization, and sequestration. Many people would use this word storage instead of sequestration. So there is a small difference between storage and sequestration. See, if you are trying to store something in the same phase, for example, CO2 is a gaseous molecule. If you are storing gaseous CO2 as gaseous CO2 somewhere else, then it's just plain storage. Okay, you're just storing it. But then when you are if you are storing it as a gaseous CO2, since it's lighter molecule, over a period of time, it would just go back to the atmosphere. So storage typically means that you have stored it, might be stored for some time, but then it ultimately might find its way to the atmosphere. Sequestration, on the other hand, basically mean that you are converting this gaseous CO2 into a form which will not go back to the atmosphere. So CO2 storage and CO2 sequestration, this is the difference over here. So when we say sequestration, we mean that the CO2 gaseous molecule gets converted into either liquid CO2 or solid CO2 or in form of a mineral which is again solid, so that it would never go back to the atmosphere. So that's the difference between the word storage and sequestration. So this is why I prefer to use this word carbon dioxide capture, utilization and sequestration, because ultimately all the CO2 which we are going to emit, we don't want it to come back to the atmosphere even if we have stored it for the time being. That is something which one has to always understand the difference between the storage and sequestration. Now, if you talk about CO2 capture, utilization, sequestration, typically we talk about this because of a general problem which we have been seeing, and you must have read a lot about global warming. Okay. Now, if you look into whatever the data shows that we should be emitting so much of CO2 from say 10 years down the line or 20 years down the line, we always underpredict ourselves. The reason is that in 2018, when this data was basically put together, at that time, people used to think that the peak of CO2 emission is going to come somewhere around 2020. And let me tell you, 2023, last year, the largest amount of CO2 was emitted. So that basically means that we are still today, we are continuing to burn more coal and more fossil fuel, and we are emitting CO2 at the rate at which we didn't expect 10 years back. We are doing it continuously at a much faster rate. India, last year, our coal consumption was 8.5% higher than the previous year. So if your coal consumption is higher than the previous year, it basically means that ultimately coal will be combusted and you are going to produce CO2. So typically in India, we are producing CO2 at a rate of 5% every year, additional CO2, 5% every year. So if you roughly do this calculation 5% every year, it basically means that within 10 years, the total CO2 emission which we are doing today, in 10 years, we will be doubling. So roughly that. We'll talk about the numbers, and before I go a little deep here, let me tell you that I don't want to be sounding pessimistic, but I will tell you the picture and you will take a call whether it's going to be a problem which can be solved easily or it's going to be a monster which will have to be tackled somehow. So that's how what I'll try to tell you. The CO2 emission is the major contributor to the climate change. So when people talk about climate change and global warming, it's mainly connected to CO2 emission. This has been almost established, and people say that it's all because of the anthropogenic release of CO2. Anthropogenic release means the CO2 which comes out from human activities. The CO2 which naturally comes out will anyway come out, but the additional CO2 which comes out because of the human activities, this is what is called anthropogenic CO2. So due to the anthropogenic release of CO2 emission, which has been increasing since industrial revolution, this climate change is the effect today, what we are seeing today. Okay, IAE data shows that last year 41 gigaton carbon dioxide was emitted around the world. Now 41 gigaton CO2 basically means, let me help you out with this number, 41 billion tons of CO2. So this is the yearly number, 41 billion tons of CO2. So this was 2022, and world over we are still today, after talking about so much of renewable energy, solar and all, we are still emitting more and more CO2 every year. And it's expected that the peak is going to come somewhere around 2030. So 2030 is going to be the peak is what is expected. So it basically means that the increase in CO2 emission will keep happening up to 2030, and then beyond 2030 there would be slight tapering off, and then we might be able to go down depending upon how do we plan our activities in near future. So that's the data. The Paris Agreement tells you that we need to be below 2 degrees centigrade compared to the pre-industrial level. So it's this number, I think the English is not clear. Below 2 degree above pre-industrial level, it basically means that when the pre-industrial level temperature was T, today you should be targeting for T plus 2 degrees, not beyond that. Okay. So the way we are going, the data tells you that if you have to be T plus 1.5 degrees, this T is the temperature at pre-industrial level, not today's temperature. Today we are already much higher than that, but if that T is pre-industrial level, if you want to be remaining below 1.5 degrees, T plus 1.5 degrees, the credit which you have right now is roughly 250 billion tons of CO2. How does this get calculated? It gets calculated today, our CO2 concentration in the atmosphere is roughly 420 ppm. Okay, so the rate at which we are emitting our CO2, in certain year, the concentration of CO2 in the atmosphere will become beyond 420 ppm. That basically means that depending upon the CO2 concentration in the atmosphere, the temperature global temperature is going to rise. Okay, so if the global temperature rise requires, you want it to be below 1.5 degrees, you currently have a credit of 250 billion tons of CO2. Basically means that if we emit 250 billion tons more, the CO2 concentration in the atmosphere will be so much that the global temperature will become T plus 1.5 degrees. And 250 billion tons basically mean, with the 41 billion tons coming out every year, is that by 20, maybe another 5-6 years, we will reach this target. Now in 5-6 years, we are hitting this 1.5 degrees mark. So basically it means we cannot target for remaining T plus 1.5, we will have to target for T plus 2 degrees centigrade. And for that, what we will have to do is what I am going to discuss today. Okay. So based on 41 billion tons of CO2 every year, the target for 2 degrees centigrade, that is 1150 billion tons of CO2, extra CO2 coming out, has to be sequestered. So that basically means that we will have roughly 23 years, some around, so by 2050, we need to basically somehow capture so much of CO2, that is 1150 billion tons of CO2, achieve the target of T plus 2 degrees centigrade. Now let's look into the number, 1150 billion tons. So how we are going to achieve it? So to achieve that target, you will have to basically reduce the CO2 emissions from pretty much everywhere. Power sector emits most CO2. After that, it's the industry, steel industry, cement industry, chemical industry, all kind of industry which basically we use in our day-to-day activity. So industry is the next. Transportation is followed by, and then buildings, cooling and heating loads in the building, and other transformation, all put together. We need to basically cut down 700 billion tons of CO2 by 2050 to meet the scenario of 2 degrees centigrade. This number comes from this here, 83%, so 800. So if you take 100%, that's minimum I will have to cut down, or we will have to cut down 700 billion tons of CO2 by 2050. And if I have to do this, 700 billion tons of CO2 by 2050, we'll have to figure out where we will be able to do that. So in power sector, you see the biggest block is moving from fossil fuel to renewables. So that is probably one of the solution, that you will have to move from fossil fuels to renewables in power sector, and then significantly large nuclear utilization of nuclear power rather than coal-based or fossil fuel-based power, and almost similar numbers of coming from CCUS. There could be many such cases where you cannot move to renewables or cannot move to nuclear. So those CO2, whichever comes out from the production of power, has to be captured, either utilized or sequestered. So this is a significant number. Industry mostly depends on energy efficiency. Transportation mostly depends on energy efficiency. Building, obviously, you can improve the energy efficiency. Other so you see most of these, if these orange blocks are very iffy, very difficult for you to really see. For example, I'll give you an example. 1980s, 60s, 70s, we used to have a car which used to run with 4 cylinders. Today we have 3 cylinders engine. But has the efficiency increased? Not. The efficiency has not increased. Okay, what has increased though, the infrastructure has developed. So for transport, if you want to go from say Chennai to Bangalore, it used to take 6 hours or 12 hours. It will now take you 6 hours or 5 hours. So that is what has basically improved. So efficiency has pretty much gone up because of the infrastructure development, not because of the efficiency of the engine itself. The efficiency has pretty much remained the same. Similar is the story for entire other industry you talk about. The efficiency has gone up a bit, but it has not been this kind of a story. So it's typically, if you look at these numbers, so what we'll have to focus on is renewable and then carbon dioxide capture and utilization. I don't want to talk about nuclear today. It will take a lot of time. So this is 2 topics which I am going to talk about quickly. I will talk about renewable because this is not the focus of today's talk. I'll mostly talk about CCUS, which is basically required in pretty much all the other sectors also. Now let's look at renewables. What is the status of India and renewables? the percentage share of electricity production from renewables, and this includes hydro, solar, wind, biomass, waste, geothermal, wave, tidal, everything put together. And this is where we are. Does not matter, this is 1985 to 2022. So we have been talking about renewables from last 20 years, maybe more than that, and what we have achieved is this. Now, probably now there is more seriousness and this might go up, so we will be able to basically reach the numbers which we were somewhere in 1980s, but still we are not there. We are heavily dependent on fossil fuel based energy and it will remain so for many, many years. And since we are dependent on fossil fuel energy, yearly emission of India is 3 billion tons of CO2. That is 3 billion tons. And I was telling you that it is rising at 5% every year. So you can imagine by 2030, 35 or around, yes. Yeah, that's what I was requesting Sabari also. But I think he is also not aware which switch will switch off those two lights. But I would request you to come over here. There is one chair here. Okay, good. Now it's better. So if you look into it, this small dip you see there, not a small dip, it's a significant dip. I'm sure all of you know why there is a dip there. That's COVID effect. Okay, so due to the COVID, you see significantly a smaller amount of CO2 was being emitted, and now we have jumped back and we are going at the same pace at which we were going. See, it's very important for us to understand, when we are growing at 7% something, the CO2 emission cannot be much lesser than that. So we are actually doing much better because of our solar installations and all. We are not emitting CO2 at 7%, but we are emitting only at 5%. So that's the advantage, but then 5% itself is a much larger number. And this is what I was trying to tell you, that we are emitting roughly 3 billion tons every year. And last year, India produced the maximum CO2, as we also consume the maximum coal and all. However, the good news is that solar installations have increased in recent past. However, the lower than our targets. I'm sure many of you would know the target of the current government was by 2030, we should have installations of 500 gigawatt of solar panel. We are not even reaching 60% of that by 2030. The rate at which we are basically doing our solar panel installations. There are many challenges. Let's not talk about what challenges we face, but the end result is that we are far behind our targets. But since I'm talking about renewable, and since we're talking about solar, we are banking too much on solar, let me give you some more data. Now, if you are trying to bank on solar, solar is available only roughly around 6 hours a day. Okay, sometime it will be 8 hours, sometime it will be 4 hours, sometime there will be no sun coming up, but roughly let's say on average it's 6 hours a day. It basically means that for the remaining 18 hours a day, you will have to store all the energy which you have produced in these 6 hours. Now, if you really look at it, two major things people talk about. One is batteries and one is hydrogen. Okay, why batteries? Because you can store all the energy which you produce, electricity which you produce during these 6 hours of sunshine, you can store all that into batteries. One has to do the calculation. Again, we have done that calculation, but I'm not talking about it. You can do the calculation how much batteries will be required for our energy need which we have. Okay, I'm not talking about that today, but let's talk about what is about hydrogen, because India is going for green hydrogen really in a big way. This is the story of hydrogen. So hydrogen is an energy carrier, is a feedstock, and it's an energy source. So hydrogen is very versatile. Why it is becoming so important to understand what is the role of hydrogen? See, till yesterday, till today, till tomorrow, any time we will be using, mostly we are using hydrocarbons from under the earth. We are digging all the hydrocarbons from under the earth. So hydrocarbons are hydrogen as well as carbon. Okay. Now, if there is a requirement that you don't have to use hydrocarbons from under the earth, carbon dioxide is anyway there in plenty in the atmosphere. You can always, science fiction, you can always capture carbon dioxide from the air. The carbon part of that hydrocarbon is available to you. What are you going to do with the hydrogen part of that hydrocarbon? Because our entire cycle depends on carbon and hydrogen. So if you will have to do anything other than fossil fuels, which is hydrocarbon primarily, you will have to rely on producing hydrogen, and hydrogen does not come from thin air. Okay, so you will have to worry about that. So hydrogen becomes a big issue. Now let's see what is the story of hydrogen when we are trying to store solar energy in hydrogen. 55 kilowatt hour of electricity is consumed to produce 1 kg of hydrogen. So if you are going to produce 55 kilowatt hour of electricity by solar panel, it would produce 1 kg of hydrogen. Okay, just 1 kg. How? By electrolysis of water. Okay, so you will get green hydrogen, 1 kg hydrogen, you will consume 55 kilowatt hour of electricity. Now, this 1 kg of hydrogen, if you want to use it for any process, right now we don't really know how to store and transport hydrogen effectively. So the next approach is that you convert this hydrogen back to electricity. Okay, and the most efficient process currently is fuel cell. If you are going to burn this hydrogen, it's even lesser efficient, but the most efficient process is fuel cell. So 1 kg of hydrogen, as soon as you bring it back to electricity, you lose almost 25 kilowatt of our electricity within this process. So the best and efficient fuel cell, which is currently 80% efficiency, they say, you are basically getting only 30 kilowatt electricity back. Okay, now this is a solar panel is over here and your fuel cell is sitting over here, then you are losing 25 kilowatt hour of electricity. But if your fuel cell, if your solar panel is somewhere, say near the seabed or seashore, and then you are having your power plant or fuel cell, say 100 kilometers, 50 kilometers, 200 kilometers, depending upon where you want to be, that far, basically you will have to store and transport hydrogen. Now, storing and transportation of hydrogen is very difficult because hydrogen is a very small molecule, does not like to be contained in a small space. So, if you are going to store and transport hydrogen, 1 kg of hydrogen will consume anywhere between 10 to 15 kilowatt hour of electricity. This is the story of storage and transportation of hydrogen. So, now how much you have lost? 25 was lost over here. 10, let's say, was lost over here. So 35 is lost out of 55. So you are left with only 50 kilowatt hour of electricity. So basically what I'm trying to tell you is that whether you are going to batteries or you are going to hydrogen, it's not free energy. Obviously you are getting some free energy, but it's not at the scale at which people talk about. If you are going to convert your solar electricity into hydrogen or any other form of energy to store it for next 18 hours, you at max you should be able to use only 30% of that energy which you have basically produced during these sunshine hours. So that's the story. Anyway, I don't want to go about hydrogen, but I am emphasizing again, hydrogen is something which you cannot get away with. Hydrogen is very important and it would be required in tons. And today the amount of hydrogen which we produce or we consume, from today 10 years down the line, our hydrogen requirement will be at least double of what we are doing today. Okay, so this is why I talked about this hydrogen. Now let's talk about another thing which is again sorts. I talked about renewable. The other thing which people talk about is like why we are worried about CO2 so much. Let's plant more trees. Very good. Let's look at the numbers there. If you want to plant more trees, if one does the math, we need to capture 20 billion tons of CO2 every year for up to 2050 to achieve 2-degree scenario. This is what I showed you. So let's see whether can we do it by planting more trees. 1 hectare of forest would sequester on average 10 tons of CO2. So if you plant forest in 1 hectare of land, it will capture roughly 10 tons of CO2. And world over, in 2020 alone, 40 billion tons of CO2 got emitted in 1 year. It's not overall. 1 year, 40 billion tons of CO2 got emitted, which is sequestered in forest would require 4 billion hectares of land. How much land we have total? 15 billion hectares. So basically we are saying that if you cover the entire earth by just planting more trees, within 4 years you will be run out of space. What you are going to do next? So whenever these things are being talked about, you will have to always bring the maths in there. The maths looks super poor if you are trying to talk about sequestering all the CO2 which you are emitting by just planting more trees. So with this background, let me come to the topic. Okay, now this is going to be a little bit more deeper. I'll still try to make it simpler for all of you to understand. So when we talk about CO2 capture, there are 2 places where you can capture your CO2 from. One which is called point source. Point source basically all those industry which is basically burning fossil fuel to produce energy, and this energy will be utilized further for the process. For example, if you are trying to produce cement, you will have to run it at 1000 degrees centigrade. For 1000 degrees centigrade, you have to burn a fossil fuel to achieve that kind of temperature. If you are going to produce steel, again you need something around 900, 800, 1000 degrees centigrade. For that, you will have to burn fossil fuel to basically do the process. So all those processes are basically done at a point, basically where tons and tons of steel and cements are being produced, or where thousands of megawatts of electricity is being produced. So all these places you will see a chimney, a stack there. The stack which you see there, so far people were only worried about SOx and NOx because these are poisonous gas. Carbon dioxide is not a poisonous gas. Let me again tell you, many people get confused saying that carbon dioxide is an environmental problem. It's not an environmental problem. It's not a poisonous gas. It's a very inert gas, does nothing to you mostly. So this is why people were not bothered about capturing it so far. But what we have done, if you really look at it, what we have done over last 100 years, we have dug all the fossil fuel from under the earth, we have burnt it, we used the energy, and all the CO2 which came out of this process, we released it to atmosphere. So this is only half the cycle. So unless and until you complete the cycle that capture all the CO2 and put it back under the earth, this is not going to be a sustainable path. So we have been living unsustainably from last 100 years, and this is what we have basically come to at this point of time. So what I'm trying to say that you will have to capture your CO2, either you capture it over here, or once it goes back to the atmosphere, like in the car and all, you obviously cannot capture the CO2 coming out from your car if you are burning a fossil fuel. It will go to the air, so then you capture it directly from the air. So these are the two places where you will have to capture your CO2. Now let me tell you what is the challenge. I'll go to the next slide, which I have tried to basically explain. Today only I made this slide so that it's easier for everyone to understand. The challenge is that this stack which you are seeing here is emitting CO2 at certain rate. Okay. In this, you see this is a ball. On top of that, it's not visible to you, but you see this is a Velcro. Okay. So let's assume CO2 is a spherical molecule over here, which is covered with a Velcro on top of it. Okay. And then you have other gases. For simplicity, these gases typically which you see over here is roughly 1 CO2 molecule and 9 to 10 nitrogen molecule. That's for simplicity. I mean, there are many other gases, but let's assume that the gas which you get from this stack is 1 molecule of CO2 and 9 to 10 molecules of nitrogen. The CO2 molecule has a Velcro on top of it. Basically means that if I bring this molecule to a pad which is also Velcro adaptable, will catch this Velcro ball. And the remaining molecules, since there is no Velcro on this, it will just roll over that particular surface. Okay. So I have brought a Velcro over here, a white Velcro with some surfaces. So when, just imagine when this gases, entire gas will go through this Velcro, what will happen to it? This molecule will get attached on this surface, and remaining nitrogen molecule will just go out. This is how we capture our CO2. Okay, why do we have to capture the CO2? We'll talk about it later. But this is very simple, very easy, because you have 1 CO2 molecule out of other 9 to 10 nitrogen molecule. Now let's see what is the challenge. The challenge is the CO2 composition in point source is 10% CO2, but CO2 composition in air is only 0.04% or 400 ppm. Okay. So if you are not capturing this CO2 from the point source where it was 1 CO2 molecule and 10 nitrogen molecule, you will have to capture it from the air, which is 1 CO2 molecule and 2500 nitrogen molecule. Now imagine the same process where this particular Velcro has to pick 1 CO2 molecule out of 2500 other molecule. So what is the challenge? The challenge is the strength at which this Velcro and these two molecules should interact should be very strong. Okay. And if the strength is so strong, it means if I have to regenerate this molecule, because I cannot consume new molecule every day, no? So I'll have to regenerate this molecule. So if I have to regenerate this molecule, I'll have to apply equally large amount of energy to separate them out. Okay. So the challenge is this, that if I am trying to do it from point source, it will be slightly cheaper for me to do that. If I am trying to do it directly from the air, I need a material which is very exotic. That has to be synthesized in a very particular way, may not have one-step synthesis. Why I am talking about one-step synthesis? See, typically if I am going to produce 1 kg of steel, I will produce 3 kg of CO2 for the production of steel, just for the production of steel. When I am mining the steel, the ore for the steel, there also I produce CO2. So all those, if you add much larger number. So if in this particular case, if I am going to produce an exotic material, which will capture 1 CO2 molecule from 2500 other molecule, you can imagine it cannot be a single step process. It will be a multi-step process. In every step, If I am going to produce 10 kilogram of CO2 or 5 kilogram of CO2, assume that there are 2 steps or 3 steps required to get this particular material. To generate that material, I am producing 10-15 kilogram of additional CO2, which otherwise was not necessary. Today, I am releasing all the CO2 to the atmosphere. I am not producing that material. But if there is a requirement that I have to capture that CO2, then I need this new material, which is not coming from nature. I am synthesizing it. It means I am putting up a plant. From industry perspective, we are making money, but it's not about money here. I am talking about CO2 neutrality. So please understand this problem, that the material which is going to be produced to capture this CO2 will also emit CO2. So this material is not only capturing the CO2 which was produced while we produce this material should also capture the CO2 which is being produced from power plant, from steel industry, from cement industry, from everywhere we talk about. Okay, so that is the challenge. This is the challenge which we have to always worry about. Now, the question is, why do we need to capture the CO2? Why can't we directly use the CO2 and convert it into some chemical? Many people will talk about, oh, we are skipping one step. We will go directly from the flue gas or directly from the CO2 in air to a chemical. We have a very efficient process. Let's look at that efficiency. So the efficiency of that is, see, what basically is CO2 utilization? CO2 utilization is, you have plenty of CO2. What you are going to do with this CO2 once you have captured the CO2? So the proposal is that we will react it with hydrogen. This is why I am talking about the importance of hydrogen. Anything you do, you will need hydrogen. And this hydrogen does not come for free. This is what I was telling you the previous slide, that this hydrogen will produce from the splitting of water, which will come from solar panel and all. And there are many challenges there. Let me tell you first what is the challenge. The CO2 and hydrogen will react to either form ethanol, methanol, formic acid, jet fuel, many things. People talk about 100 different compounds which will form. But ultimately the reaction is this simple reaction. One CO2 will react with one hydrogen to produce all kind of chemicals with some catalyst, some temperature and pressure. But the challenge is, this currently is maximum efficiency is only 25%. Now there are 3 different routes by which you can convert this CO2 into a chemical, either thermochemical or photochemical or electrochemical. Okay, there are 3 different routes. Thermochemical is roughly 20 to 25% efficient with 100% CO2. Electrochemical is roughly 15% efficient with 100% CO2, and photochemical is roughly 5, 6, 7% efficient with 100% CO2. So now you imagine, if someone is telling you that I will do this reaction with 10% CO2 and 90% nitrogen or 400 ppm CO2, you can imagine what will be the efficiency of the process which they are talking about. And these processes are not at room temperature. These processes are at 500 degrees, 600 degrees, 700 degrees, 800 degrees. So please be aware that this is the story of CO2 capture. So anyway, the challenge is that once I have captured the CO2, the cost is given over here. If you are going to capture CO2 from point source, it costs roughly 30 to 50 US dollar per ton. This is also the cost in India, roughly 50 US dollar per ton for CO2 capture. That, please also understand that we are producing almost 3 billion tons of CO2. Just multiply this number with this number and see what is the amount of money which would be required to make each of us sustainable. Okay, but then let me quickly move on. I think I am taking too much of time. See, if you have a 500 megawatt power plant, CO2 capture alone will consume 25% of that energy. It basically means that if you are going to go to a sustainable electricity, 500 megawatt power plant will become 375 megawatt just for capturing the CO2. And once you have captured the CO2 and you are going to utilize it or sequester it, it will be another 25% of cost. So basically it means that if you are getting your electricity today at 10 rupees or 12 rupees per unit, you should be ready to pay 25 rupees per unit if you want to be sustainable. And also if you are not paying it, it's not that we are very smart. If we are not paying it, we are basically borrowing that money from our future generation. It's as simple as that, because this is the depth in which we have to die. This is the right price which we are not paying today. We are assuming that this will not affect this earth, and this, by assuming this, we are basically trying to say that we are not bothered about the future generation which is going to come. So we basically are borrowing this money from someone else. Let's move on. So once we have captured the CO2, now we have pure CO2. I told you what is the challenge with CO2 utilization. Even if you know a right process, if you have all the energy economics worked out, all the CO2 which you are going to produce every year from India, say we produce 3 billion tons, you cannot have a market for it. I'll tell you why. See, the cost of CO2 is $50 per ton, that is roughly 5 rupees per kg. Okay. Now, if you are going to utilize any chemical, you will have to add hydrogen to it. Currently, the green hydrogen cost is roughly 300 rupees per kg. So, you are getting 5 rupees per kg CO2, 250, 200, 300 rupees per kg hydrogen. These are the cost of the raw material. Now, what will be the cost of your product? You do the calculation. And you tell me, are you ready to pay 300 rupees per liter diesel or oil or anything today? Not possible. Okay. So, it's going to be 3 times. Who is going to buy your chemical? Even if you are converting it into a useful chemical. And let's say there is one day on this earth, everyone will be able to pay whatever they want. Still, you cannot utilize all the CO2 which you are going to produce. Only 15% maximum you can utilize. So, remaining 85% CO2 has to be sequestered. There is no other way out. And if you are going to sequester the CO2, you cannot talk about, if you go to mostly businesses, they have a very fascination of saying that we are going to monetize this problem. There is nothing to monetize here. What you will monetize? So, the problem is that CO2 has to be sequestered, it is going to cost you money, and the infrastructure has to be developed, because we are talking about it from last 10 years, and I don't really see any infrastructure which is being developed in India at least, where we can say that we are going in that direction or moving in that particular direction. So, I will talk about a few more slides before I basically end the talk, so that we can discuss further. See, the CO2 capture part, as I was telling you, that exotic molecule. If you look into, I don't want you to read through it, don't worry about that. Okay. So, what I am trying to tell you, that if you look into the literature in academia, people are very much fascinated with something called metal organic framework or similar molecule which will basically capture CO2. So, the story of that is, I might be able to do, if you do the literature search, you will figure out that per gram of metal organic framework, I might be able to at max capture 1 gram of CO2. In reality, it will be 0.1. Okay. So, if I am going to capture 1 gram or 1 ton of CO2, I need 1 ton of this particular material. Okay. Now, the question is that even if I have to capture 2.9 billion tons of CO2, I will have to, I need at least one may need 2.9 billion kilogram of MOF, and then regenerate is 100 or 1000 times. You will have to regenerate is at least 100 times or 1000 times, depending upon what is your energy, the capture capacity. Okay. Today, these materials, when people talk about, hardly they can regenerate it 5 times, 10 times. This is where we are today. Okay. In terms of science. Now, this is something which has been implemented from last 50 years. Typically, natural gas which we use, those days for 20, 30 years back, it used to be pure natural gas. You drill a hole and you get tons of natural gas, you just burn it. Today, most of the fields have become quite sour. It basically mean that you have methane and you have a lot of CO2 also. So, this is a process which is well known. How do you capture CO2 from a gas mixture? And this is being done by monoethanolamine. This is kind of a chemical which is a wonder chemical. People talk about in industry, will talk about in industry, will say everything will be solved by monoethanolamine. Okay. So, monoethanolamine or diethanolamine, triethanolamine, there are compositions, mixtures of these chemicals which are proprietary chemicals. People will sell you for multiple $100 and all. But the challenge is here this, let me tell you, I have already brought it to your notice. See, monoethanolamine is not coming again from thin air. This is a chemical which you will have to generate. If you have to capture this CO2, with the CO2 from a power plant, so I need this chemical, but this chemical is not coming from thin air. I have to generate it from some 2 other raw material. The other raw materials are ammonia and ethylene oxide. Okay. Now, I don't know, any one of you know what is the temperature and pressure at which ammonia is being produced. It being produced at 300 plus bar and 300 plus degree centigrade. Okay, so this is a very high pressure, high temperature process. So, do you think ammonia will get produced without any CO2 emission? Okay, and the emission, the CO2 emission for the ammonia, NH3, it's not only nitrogen which is required, hydrogen is also required there in that ammonia. And I was talking about that hydrogen problem. Okay, nitrogen you will get from the atmosphere, but hydrogen where you will get? You will again get from the same splitting of water. Okay, at that kind of temperature. So, today all the ammonia which we basically get in the market is black ammonia, gray ammonia, which I am giving you a color because hydrogen, the color of hydrogen which is used there is black or gray. Black or gray hydrogen basically means that it has been produced from a fossil fuel rather than from water splitting. So, imagine this was the cost of $50 per ton by using monoethanolamine, which is being produced from black ammonia. Tomorrow, if there is a regulation that all the ammonia has to be green, you will see what will be the cost of monoethanolamine which will get produced. Okay. Ethylene oxide. Now today we may talk about, we will do all this problem, we will solve it, but ethylene oxide, the only source of ethylene oxide today is the fossil fuel, the same fossil fuel which you don't want to produce. There is no other source of ethylene oxide. The only other source of ethylene oxide is to plant trees and then convert it into ethylene oxide. Okay, and I gave you the story of trees, how many trees we can plant on this particular earth. So this is the challenge. If I have to produce this chemical, it may look like I have solved the problem, but it has not completely solved the problem because we have not solved the problem where it has to be solved. Okay, so these are the challenges. Let's not worry too much about though, but these are the challenges under which we work. Okay, we still work on the same kind of problems. This is the largest direct air capture unit, which is called Orca. Climeworks is the company which basically has built it in Iceland. Okay, this is largest unit. It has a huge footprint. It may not be visible from your slide, from the slide over here. It captures, you know how much? It captures 4,000 tons of CO2 every year, and which is equivalent to 1 second of global CO2 emission. Okay, this is done at a cost, you know what? $200 per ton. This is what they claim. It will be higher than that, I'm telling you. Okay, I'll give you another example. This is an example of a plant in China. This is not even 10% of the plant which is shown over here. And this captures 100 and, oops. Okay, I think this is at the bottom. Anyway, this captures 160,000 tons of CO2 every year. Okay, a point source capture. Obviously, as I was telling you, it's easier to capture it from a point source. 160,000 tons of CO2 every year, which is equivalent to 2 minutes worth of CO2 global emission. Okay, and this plant will be bigger than the plant which a 500 megawatt plant will run. So that's the kind of footprint it takes. Anyway, so we look into all this, and even with all this, we basically look for a solution. We have a solution in our lab, but it works only for certain cases. For example, when the CO2 concentration is beyond 25%, it works for that. So we have nothing other than water. Why it works better? Because I am not synthesizing a new material. If I am not synthesizing a new material, then I am not emitting that CO2 which will come along with the synthesis of that particular material. So if I am just using plain water, even though the efficiency is poor, I am not emitting extra CO2 during the synthesis of this particular material, and it works out. So we have basically a demonstration unit now. One of my students is working on that. This is another, again, amine based process. Another student sitting here is working on that. So basically we have designed the molecule at molecular scale, then we looked at lab scale, and then ultimately we are at pilot scale to basically test out some of this material, how much CO2 can be captured, at what rate it would be captured. See, the challenge in these cases are that if you talk about 3 billion tons of CO2 being emitted every year, it basically means that we are talking about a material which should be able to capture this CO2 at the rate it is being produced. The rate of CO2 production is huge. Okay, so you need a material which should be able to capture within that fraction of a second when it is the CO2 is being produced. If this material will capture 1 kg of CO2 in 1 hour, then that's not a solution. Okay, this material should capture 1 ton of CO2 in 1 hour. Then only we are talking about a solution. We are not there yet, but yeah, we are working on some of those technologies. We are also looking into direct air capture, where we have a process. You see here, in this particular room, we have the concentration measurement, monitoring of CO2, humidity monitoring, temperature monitoring, pressure monitoring, and then we basically pass that CO2 into this reactor. So when the CO2 goes in at around say 700-800 ppm, by the time it comes out, you will get from here around 0 ppm of CO2. Okay, so this is directly capturing from the air. So some of these technologies are already at TRL 8-9. TRL is called technology readiness level. If it is at 8 and 9, it basically means that it can be directly implemented on the site. So this is a project which we have recently delivered to L&T, and they are building hundreds of this unit to be put on site. The site which they will not disclose, but ultimately when it comes up, all of you will be able to know it. So the second point which I wanted to cover in another 2 minutes probably is the captured CO2, what I am going to do with that. Okay, so we also have demonstrated what you are going to do with this. Is a gas hydrate of methane which is sitting under the seabed, And similar gas hydrates of methane are found around the world. These are methane inside a hydrogen bonded water cage. Basically, you must have seen ice. Ice is nothing but its hydrogen bonded water molecule. It forms a cage like a structure. Okay, so when we talk about a cage like a structure, we mean that this is a cage where there is some space in between. So hydrates basically are similar cage like a structure, very much similar to ice. The only difference is that here the cages are slightly bigger, and when the cages are slightly bigger, it can actually occupy a guest molecule inside, and the methane or the CO2 can become the guest for that particular cage. Okay, so in the process, what we are trying to achieve is that a molecule which was gaseous, which was mobile, we have basically made it immobile by putting it inside a cage. Okay, so this is what is there. Millions of years these hydrates exist and it does not dissociate, because under the seabed you have the right temperature and pressure conditions where these hydrates will exist as solid hydrate. Something very similar we are trying to do. We are proposing that 100 meters to 1000 meters below the seabed, not in the water column. 100 meters to 1000 meters below the seabed. These are unconsolidated sediments. Basically, unconsolidated sediment means the sediments which are mostly sand has not got consolidated. So there will be pores. Within this pore, there will be water. Water could be fresh water, water could be salty water, any kind of water will be there. And then what we propose is something like this. So this is something I'm sure many of you would have heard about: shale oil, shale gas. These are produced by fracking, which is basically a rock is fracked 1000 meters below the surface of earth. So for that, what we do, we basically supply a very high pressure water and we create cracks, and then we release the water, and once we release the water, all the oil which is there in the cracks will come out and you will start producing it. So basically fracking is to release the pressure or really make it more porous so that oil can come out from the internal pressure. This is exactly opposite of that. What we are trying to do is that we are going to frack it, but not to produce something, but to basically sequester something. So here you will be basically putting the CO2, water is already there, the temperature is already there, the pressure is already there, and if I expose that water to CO2, it will get converted into solid hydrates. So we have a pilot plant for that as well, where we have done all these studies, and then that's all I have for you today. The experiments work which I have discussed last few slides, many of my students are here, they have done it, and others who are you see here, they are doing it. I don't do any experiment, I only give lectures. But the other discussion which is mine, I'll take all the responsibility of whatever I have said over here. Thank you very much. I am now, the floor is open for any question. I have deliberately tried to finish it off a little early. How are we going to change? Yes, very, very pertinent question. But was that a comment or should I answer that? Okay, let me answer what I typically answer for such things. See, the problem is the way we basically measure our prosperity is based on GDP. Okay, forget about attitude. Tomorrow, today, every day you will see in newspaper, everyone would be talking about that our GDP is increasing at this rate and this is where we will go and all. What exactly is this? If you are not consuming and if I am not consuming, then how the GDP will increase? It will not come from thin air again. So now if we are consuming, and this is what we are trying to do, we are trying to consume more and more, and that is going to basically improve our GDP. So there is a contradiction, no?
So, but we are not talking about the grassroots happiness, no? Instead of, to.
You are talking about it. But how many of us are talking about this happiness quotient? Yes, I know, but how many? I might asking another question. I know all this. I'm talking, see, I'm an engineer, I'm not a humanities professor or a chemistry professor. Let me tell you, engineers are practical people. Okay, we will only talk to you things which is practical.
Sir, with due respect, technocrats should have a social responsibility.
Sir, I am not
Sir,
saying
I'm
that
very
what you are
expert in
saying is wrong.
technology.
Let me tell you what is practical. I agree, I get all your point and I
A
agree with you
technocrat should
completely.
become it should have this much more than responsibility. Then only it can become.
No, that's fine. Yes, I see, this is why I'm not here to preach. Please understand. I am here to only instruct and teach. Okay? What you are saying is preaching, which I don't do. In IITM, no faculties does preaching. See, that is something which you will not be able to do. But I'll tell you, I'll give you your answer. See, the question is, I know there are many people who wants to do this. The solution is not there though. Okay, because you cannot change. You can change yourself, maybe 5 other people, but can you really change the entire world? You cannot. So the solution, as an engineer, what do we give a solution? We say, okay, fine, whatever you are doing, we will try to solve your problem. It's like a doctor. They will tell you, you do this for all the people who have cholesterol here. The doctor tells them run every day 5 kilometers. Do we do that? We don't. We prefer to take that pill in the night with that 110 milligram or 20 milligram, depending upon what is your age. I take 10 milligram. So this is what I'm trying to tell you. This is how we have become. When we were a small child, we used to have 2 pairs of clothes, 3 pairs at max. Hardly we used to wear a slipper or some shoes. One school shoes, that is what we will wear for the entire day. Today, go and look at your kids or your own wardrobe. You will have 50 pairs of clothes. You will have 10 pairs of shoes and slippers. So, are you not committing the same mistake what we are trying to preach? It's there. I'm not telling you. I'm telling every one of us is culprit of this. So, what you are telling is right. That it's our greed because of that we are here. But unfortunately, this greed has become so deep that it's very difficult for you to change by just preaching. You will have to do something more than that.
Sir, I have a question. Some of the statistics that you have mentioned are so telling, so mind-boggling, that I'm sure regulators are going to take notice of this. They are aware of it. What do you think should be the right regulatory interventions to solve this problem of excessive carbon emission, control of emissions, sequestration, and all that? Do you think regulatory intervention will help? If so,
no doubt. Actually, 10 different interventions are required. But I'll tell you what is the challenge here. The challenge, people are knowing it. There is technological solution. But I'll give you another data. See, in India, it's said, I don't know, sir would tell you better, it said that 400 million people in India cannot afford electricity today. So many of them don't have electricity, or many of them get the electricity because government give them for free. Now the question is, I gave you the data that today we are paying 12 rupees per unit. And if we are going to implement any one of these, it is going to become say 25 rupees per unit. So now you tell me what government will do. Can it be solved by a regulatory framework? Somewhere someone has to pay for it. The question is that who is going to pay for it has to be taken up. See, till 2-3 years back, we were paying 100, 200 rupees for our gas cylinders. And we were still complaining. Governments were coming up and going down because of the gas cylinder price. Today we are paying 1200 rupees. We are affording it, no? Somehow 6 times we are paying. So I am just trying to tell you that we have to change our mindset. Every time we go out and start breaking, it's becoming too expensive, we have to see and we have to acknowledge that whatever cost we are paying today, we are basically borrowing in from our future generation. We are not paying the right price. I'll give you another example. Sugar, 1 kg of sugar, how much we pay? 35, 40 rupees, 45 rupees at max. You know how much water gets consumed by 1 kg of sugar? Just imagine a number. Or rice. Rice production, 1 kg of rice requires 3,500 liters of water. 1 kg of sugar requires 3,000 liters of water. Are we really paying what we are consuming? We are not. We are used to getting everything for free because Mother Nature is giving us for free. We are not questioning ourselves. How long you will do this? This is the question. So obviously, this earth is having enough for our need. But as he has rightly pointed out, that's not enough for our greed. We have become too greedy for everything. So this is how it will be ultimately. So I'm sure the only solution is regulatory solutions and all, but has to be implemented. One has to do it one by one.
In addition, Professor, very nice presentation. You just mentioned nuclear energy, but isn't it safe, isn't it time that we look at it seriously, because that appears to have the solution for many of the problems that we face. First of all, it just eliminate CO2 at all, right at the source.
I agree with you completely. This has to be brought in and being discussed. Actually, even in ITM, we have been discussing about it multiple times. There is a time that we should go for micro-fast breeder reactors and all. These technological discussions are happening. But I'll tell you, there is other group of people who also talks about it, and I times agree with them. See, let me tell you another philosophical. Again, the preaching came, the discussion, so I'll try to go a little bit more philosophical. See, whatever we see about this CO2, what exactly it will do ultimately? It will ensure that human civilization will not exist. Okay, What a big deal about it. The plant civilization will exist. All the animals which is all around will probably exist. So the question is that if we go the path which we have taken, it's not that a poisonous path that we will eliminate every civilization. The plant kingdom will still remain, most of the animals will remain, and humans will come back after some point of time and all. There might be a deluge and then people will come back and again. But with nuclear, the question is, are we going to go in a direction which will be irreversible for pretty much everything? So that is a question which people do ask, and you will have to, and I read huge amount of our Vedas and all those things, and there has been lot of this kind of discussions which has gone in. So if you really read through those things, you will try to be little bit more skeptical about some of these solutions. But no doubt, it's a solution which looks pretty reasonable and should be able to basically solve some of these problems. But again, I'm just trying to caution you that these things are also there, one has to look at. Yes.
US government sponsored $10 billion. University of Texas took over, collected the carbon from the petroleum industries and pushed under the salty aquifers.
It's still going on.
Is still any update on that? Because it's about
It's still going on, yeah.
two decades. It's $10 billion.
Yes, it's still going on. But these are minuscule.
Oh, okay.
Very little. For that matter, if it is going into aquifers, it is getting sequestered. But if it's going into oil fields, which is called EOR, it's not considered a CO2 sequestration though.
No.
Okay, so all the CO2 which is going down, hardly 5% remains there and remaining comes back actually. And it brings another 10 tons of oil along with that, which will produce more CO2. So EOR, that is enhanced oil recovery, is not considered as CO2 sequestration as per today's standards. Sir, you had
Carbon credit, can you throw some light on
I will
carbon
talk
credit? How to credit it and how much?
Sure, I will talk about it, sir, certainly.
Professor, that was a very brilliant analysis which you gave regarding the solutions you are trying to find, the different processes you are developing. What is the research work going on to reduce the emission at the source itself? Take, for example, the steel plant or the cement plant, where the manufacturing process itself can be developed in a manner that the emission itself gets reduced at the source itself. Is there any research work going on in this?
Just, I'll tell you what is the challenge there actually. See, for example, the ores which we were getting 20, 30 years back was having, say, 1%, say, let's say steel manufacturing, had some 1, 2%, 5% iron. Today, the concentration of iron has gone down, the concentration of copper has gone down, everything has gone down. I'll give you an example of solar panels. People are so fascinated about solar panel, call it very green and renewable. Solar panels are produced by silicon. Okay, you will have to mine 1 ton of silicon to produce how much gram? 500 gram of silicon, which will become a solar panel. So this 1 ton of silicon silica has to be mined, okay, has to be melted at how much? 2000 degrees centigrade to get 500 grams of silicon dioxide, whatever basically is required, which is not even the requirement. That is to produce metallurgical grade silica, which is 99% pure. Okay. Now, if you have to produce electronic grade silica, you will have to have tons of this kind of material by doing 10 times that previous step. And then this material has to be again melted at 2000 plus degrees centigrade. And then it has to be crystallized as a single crystal slowly so that I can cut wafers from it. Again, 2000 is 99.99%, and not only silica, then germanium and all other very critical minerals goes in there, and all of this comes from the same root. So now you imagine how you will reduce the CO2 emission at the source.
So even in the case of solar panels, the efficiency will be very low.
No, but still it produces for next 20-25 years, so people don't bother about it. But I'm just trying to handle the question at the source. See, the problem is that technology is there. But if the raw material itself is so limited, for example, lithium, someone said that in Jammu we have got so much of lithium. You know, it's ppm level concentration there. If you are going to separate out ppm level concentration from there, you can imagine how much energy will go into it. So the problem of this energy is not going to be solved. It cannot be reduced from the source. The only option for us to go to a process slowly, obviously it cannot happen overnight, slowly, which is more renewable. And solar is probably the only option right now, whatever is feasible. Even if I am getting 20 kilowatt hour per panel or whatever is that number, I'm still getting it for free.
Best thing is to develop good competence.
That is what we have been doing throughout our human history. It's very last 100, 200 year only we have done all this.
How much nuclear emits carbon? Nuclear plants.
Nuclear plant is very, very good in terms of CO2 emission. Very, very good. There is no other technology. Solar and all is much lower in terms of CO2 emission overall. So nuclear is that. And he had another question on carbon dioxide credits. Carbon credits. See, carbon credits are what? Basically, government tells you that if you are going to spend so much of money to capture the CO2, I'll pay it back to you. That's all it is. So now you can take a call. Some government, depending upon where the money will come, government don't do business. They get money from your pocket. They will bring it out from one of your pocket and put it back in the other pocket. So you will take the call, whatever you are ready to pay. Government will ask you only, how much you think I should pay? You will tomorrow say, no, don't pay anything. So you will have to decide. In US, right now in Europe, they are paying. For example, in Europe, $70 per ton is being paid. US has recently saying that $185 per ton of CO2 capture from directly from there, we will pay you for free. $185 per ton. They have that kind of money which they are able to take out from their own people. If you are ready to do that, no problem. This is what I'm trying. The cost is 25 rupees per ton does not mean that it has to come from this pocket only. Even if it comes from this pocket, you will not. No one will question you. You have to agree though.
In Copenhagen, America has agreed to pay something like $100 billion to the.
That's what I'm saying. So this is the dollar which you're talking about. The good thing with America is that they can keep printing the money and still their dollar will go up. If you do that, your currency will go down. This is the problem there. You cannot follow US always. You have ever seen, they keep printing money and then their dollar keep going up. Yeah. That is not possible with our Indian economy. If we keep printing our money, it keeps going down.
You will also have to find out how much energy is consumed in all these capturing processes which you explained.
Yes, this is why I talk about CO2 capture directly. Energy consumed means CO2 emitted. So this is what I was trying to tell you, that we have to, if you are talking about net zero CO2 by 2070, our Honorable Prime Minister has set this target in World Forum, basically mean that we have to always look at whether any process which we are talking about is CO2 neutral or not, or when it will become CO2 neutral. Then only we will become net zero CO2, otherwise it's not possible. So this is why my focus has always been to talk to you about no economics, no energy, only CO2. Every step which you do, you have to see how much CO2 you are emitting. That has to be always the focus of if we are going to reach that target. And it's not going to be unlike any other promises of government which comes in their election manifesto. This is the one which you have told to the UN. They will question you and they will penalize you for that. Next year they will ask, what you have done? Have you done something? No. Okay, then we will cut so much of funds coming from that. So there you will have to always honor whatever you have said. And once you have said it, we have to honor. And this is the challenge which all of us has to face.
So one part I want to tell you that in the Rajya Sabha recently, I think when the Parliament was in session, RKC made a statement that they have surpassed the target which they have given for the solar generation. It's already 75 gigawatt.
But our target was 500 gigawatt by 2030.
Not 500.
500 by 2030.
We will never reach.
That's what our target, internal target is that government wanted 500 gigawatt by 2030.
And that's part of the Punjab strategy, updated nationally determined.
Sir, you had some question.
Yeah, in what?
Oh, thank you, sir.
Thank you, Professor, for this absolutely brilliant analysis and the staggering figures that you've presented to us.
This is all real figures. I am not trying to put any spice on that.
Absolutely. No, my question, of course, given my professional background, was what's the options we have for nature-based solutions? In the sense, you dismissed right at the beginning, for lack of land availability, afforestation would probably not be the best option. But in terms of cost considerations, I would like to know from you, how does it stack up against
there
these
are
technological
many solutions which are basically microorganism based conversion of CO2. So you basically have CO2 eaten by a microorganism and they will produce methane in return. You are from forest department, you know many such microorganisms exist, enzymes, bacteria and all, which will be able to do that. But I am always trying to caution people on such things. It's not that you should not do it, you should certainly do it. But the scale at which we are talking about, the rate at which we require this convergence to happen, bioprocesses are not that efficient, unfortunately.
In terms of cost, simply in terms of the investments
Cost,
required.
see, you can do cost, but how much? 1%, 2% of total, 3% of total? It's about the quantity. It's not about the cost. See, the amount of CO2 which is being emitted every day, it's not about the scale. See, we have been talking about this CO2 from last 20 years. Most of the technologies are being implemented today also. Why it's not working out? Because every implementation has been at a scale which is minuscule. Don't really bother. In India, we have at least 50 such pilot plants. They are doing 20 tons capture, 15 ton capture, 16 ton capture. They are producing thousands of tons and capturing 20 tons. Is that a solution? No. This is what I am trying to bring. I mean, I know every solutions are there. We will do it. But the scale is a challenge, which we have to always understand. So bioprocesses will work. I'm not saying it will not work, and it should also be there. But the thing is, it can only change 10% of your total problem. The remaining 90% of the problem would still be there, and you will have to identify ways to bring that also under control.
The root cause is the population. Without reducing population, keep on producing energy.
This is again a preaching. That's what I'm trying to say. I don't think anyone can preach all this to anyone. Whom you will say that you go and kill yourself.
In 75, we had a red triangle during Indira Gandhi period.
The finite bird, we cannot have infinite population.
I agree, sir. I agree, sir. No problem with that. I completely agree with finite world. We cannot have infinite population. But who is going to control this? Do you have the power to say this?
Tamil Nadu controlled last 2 MP6. Punished,
Professor,
Before that, Sanjay Gandhi tried controlling it. You know what happened. So let's not go into all those details. And in
Professor,
China, they tried controlling it and they have gone back. All kind of challenges are there. We cannot be always unidirectional. Yes, sir. You have.
good evening, Professor. Thank you for a very interesting talk. I must confess, a lot of what you said was the first time I'm hearing and trying to understand what you were saying. So if the questions are a little dumb, please.
No. Please don't mind. See,
please
I
pardon me.
might be little, I would say loud, but don't worry about that. I don't.
So
not
if I
mind that.
understood right, in the goal of or the direction of your research is to improve the efficiency of capture and the efficiency of sequestration. Am I right?
Yes.
And what happens to finally the sequestered carbon? I mean, is that an ecosystem in itself? It gets into the. I mean,
No. So
does it
this
get,
is why I use the word sequestration. Sequestration basically means that the CO2 which was in gaseous phase has been converted into a solid phase. So it will remain. When I gave a solution, obviously this is just one of the solutions. There are many such solutions.
that's the one that goes into the
100
ocean.
meters to 1000 meters below the seabed. So it will remain there for geological time scale. Geological time scale, why I am trying to tell you that you don't know what would be the temperature 1000 years down the line or 2000 years down the line or 1 million years down the line. So at that kind of conditions, you don't know what would happen. But within the time zone which we know, these things will remain under the earth.
Thank you.
Professor Nadu.
Yeah.
See, I don't know whether I missed it, but did you show any calculations for the sequestration compared to, you showed calculations for why a forest cannot work and things like that. So if you can just highlight.
See the difference there, I'll tell you. Why there is a challenge with the forest. 30% of our land, see we are basically talking about a sphere, and we say that in this particular sphere 70% is covered by water, only 30% where you can plant trees. And this is only surface. But when I go deep down in bulk, I am saying 100 meters to 1000 meters. It's not surface. If you talk about layer, 900 meters of layer.
No, absolutely. Space is available. Just the cost calculations.
That's what I'm trying to tell you. I'm not bothered about cost today. If you are going to leave tomorrow, you have to not bother about cost today. This is the biggest message I'm giving. I'm telling, don't keep cribbing about the cost. You are already paying dirt cheap price for everything which we are enjoying today. We are not supposed to enjoy the kind of thing which we are enjoying today at the price which we are enjoying.
Sorry, not the cost specifically, but the amount of carbon that you
See, the CO2 has come from under the earth only, no?
Right.
So if we are putting it back, we should assume that all the CO2, it should be able to put it back.
Okay.
That's the kind of calculus. But those numbers are there.
Right.
there are these numbers which tells you that for next 200, 300 years, all the CO2 which will produce can be put down.
Correct.
So
I'm
that is
looking at
the
practically whether this you can ever propose and make it happen. That's what
I'll tell you, lot of things has to go. For example, whatever I've said here looks very simple. But even if you have to do one field trial, you know how much it costs? A one field trial for CO2 sequestration project?
no idea.
1,000 crores rupees.
Okay.
1,000 crore a minimum for doing a field trial for CO2 sequestration. Field trial, I'm not talking about commercial. So this is what I'm trying to tell you. These are the scale at which we have to identify the solutions. This is this is why I use the word monster. This is a monster which is too huge. We have to somehow manage. No perfect
Sir,
solution is there. Yes, sir.
sir, I have two questions, sir.
Please, sir,
First,
ask three.
how India is progressing in carbon sequestration, and second question is what a common man can play in this process, sir. Thank
Very
you, sir.
good question, sir. See, that person who was sitting here, he has rightly pointed out that the first thing we have to do is to basically tame ourselves. Whenever there is a sale, we should not be just going and buying it. So that's the kind of thing which we'll have to do. What we have to do is that realize that every step we take, we basically emit CO2. So just be aware that CO2 emission happens from everything. Okay, people might say that, okay, you are not using paper, you are doing it in your mobile, that also emits CO2. So the question we have to ask ourselves, how much we should be able to contain our need so that the total amount, because even if you can contain 5%, 5% is such a small amount. You can imagine 5% reduction will mean that we would no more be emitting more and more CO2 every year. That's the rate at which we are increasing every year. So if I say that I will somehow reduce 5% of my CO2 emission, then I am saying that I am no more contributing to the CO2 rise in atmospheric CO2 rise. How I can do it? If I have to go to Bangalore, let's take train, not go by flight. If I am in Bangalore, let's not try to do 2 meetings in 2 days and go twice by flight. Stay there somehow, finish those meetings and come back. These are the ways which we have to do, cut down our CO2 emission. There is no other way out. If you are, say, a person who does concerts and all, so when you are going, or you are a player, you go and play, a tennis player goes and play in Bangalore, hopefully he should be able to play 3-4 games together rather than doing every other day from Chennai to Bangalore. So all these things are simple steps, which, for example, the easiest for you is to take train, not by flight. That cuts down your CO2 emission by 10 times. Vande Bharat.
Sir,
IPL home matches can be played continuously, not like shifting.
Yes.
This is a simple example.
And also CSK should not go to Bangalore by flight, by train. Vande Bharat. One coach they can book and go. No, what is the big deal? 4 hours it will take, 4.5 hours. Anyway, it takes 4-5 hours if you go by flight and all. But your CO2 footprint is much higher there. So yes, that's a very good solution. We are talking to CSK about this actually.
sir, good evening, sir. It was a wonderful lecture and very important topic. For the benefit of students, I'm asking, can you list down all the methods which are available for sequestration? Like just a list. So for then, one more question is, we are having so many greenhouse gases. What about the other gases also?
See, the greenhouse gases are, other than CO2, are methane, which is of prime concern. And this COP, it was already decided that every country will monitor fugitive emissions of methane. And if they are not able to bring it down, then they will be penalized. So methane is the other prime gas which you need to worry about. Unfortunately, for an agriculture-based company like country like India, where there is huge amount of cattle, huge amount of agriculture product, CO2 methane emission is significantly high. What you will do about that? As someone was saying, we don't need this kind of population, but unfortunately we can't go and kill people, no? So that is something which has to be maintained. Slowly it will improve. There are other greenhouse gases, including vapor. Water vapor is also a greenhouse gas. But all these are not at an amount which is staggering. The CO2 is primarily quite staggering in nature. Methane is also a big deal because natural gas production will emit huge amount of methane. Coal production emits huge amount of methane because these gases are there present in the process. So it emits a lot of methane. This is what world over people are trying to contain. These challenges are there. When it comes for CO2 sequestration sites, CO2 can be sequestered in coal bed. CO2 can be sequestered in aquifers. Now, aquifers challenge is that the aquifers basically mean the water bodies which is under the earth. Now, would you allow people to put high pressure CO2 under your butt? They will say, oh, tomorrow if it blasts, what will happen to me? So those challenges are also there. So there are solutions, but what is under the seabed will work better, which is under the earth may not work that better because there will be huge amount of negative perception about it, like nuclear someone talked about. There is a huge amount of negative perception about it. You will have to basically convince everyone that what we are doing is good for you. Then they will say, well, good for me means what? Is it not good for you? So this kind of question comes. You have already seen what happened to this sterlite copper in Tuticorin. So these things actually is true. The entire copper which was produced there in Tuticorin was consumed by someone else. And people of that particular region actually paid for all the environmental pollutions and stuff. So,
I just want to read something because I read it. One vegetarian day per week, 52 days a year can save nearly 100 kilograms of CO2 per year.
very true, sir.
So this is what they're saying.
I'm a vegetarian, by the way, so I would always agree for it. But the problem again is this again that okay, there world over people are. If you have the data, you know, 90% people are non-vegetarian. Yeah, 90% people are non-vegetarian. So this
I
is the
would.
reality.
So we are basically looking of land-based emission of CO2. But if you look into the sea-based emission of CO2, the sea animals and the sea underground, it is also emitting CO2. And another is I would like to challenge the assumption that CO2 emitting, it will spoil the environment. Maybe that assumption may not be true after all, because if you go back 100 years before, then also CO2 would have been higher. Nothing happened. So these two, how would you go about?
I agree with you completely. There is nothing to discuss over here. Obviously, CO2 emissions are not going to be a big challenge because CO2 is not a poisonous gas. And 400 ppm, 500 ppm is not a big deal. But you will agree, based on the science, it's very clear that if your CO2 emission goes to 550, 600 ppm in atmosphere, it will start affecting you. It will also affect the temperature, the global temperature. It will also affect your health. So now the question is that should we wait for that to happen and then only we will agree that this is happening? By that time you can't look back. So the question here is that we know I can put you in a room where I expose you to 1000 ppm CO2 every day and I can analyze your entire health conditions for next 5 days and we know very well that it is affecting you. So the question is that till we reach there we start solving or we should start solving today. This is the only problem.
What about the ocean surface which are...
Sure, sir, it is there. What CO2 we are talking about is anthropogenic release of CO2. The activities which humans do emit significantly large amount of CO2. That is what we are trying to target. And that is 3 billion tons, not the one which we are emitting out because we are surviving or the animals are emitting out because they are doing their day-to-day activity. It's the CO2 which comes from industrial processes which otherwise was not there. That is the number people are talking about.
But that we can control, but the CO2 emission from the ocean...
Sir, those CO2 is naturally getting captured. You don't have to worry about it. See, it's not that in nature there is no way to capture CO2. Nature knows how to capture CO2. If you are emitting at 1 kg per hour, probably it will capture it. But if you emit 100 kg per hour, how it will capture? This is the challenge.
What was underground is mined.
See, you are mining
Chemicals
tons and tons of this oil and gas. No, billions of barrels are you are consuming oil which is there locked under the earth. This is carbon and hydrogen. Now you are burning it and you are putting it in the atmosphere. So you are saying that this CO2 is not going to be difficult for us to manage? It will be.
Which one put the hole in the
And what about volcanoes emitting CO2?
Obviously, all these are there. Can we be God there? Obviously, we cannot. What we can control, we only talk about that. We cannot control volcanoes, we cannot control anything else. There is no point in talking about it. What we can control is the CO2 which we are emitting. We know we are emitting. That is what we are trying to control. See, if you say that a volcano anyway emits so much, let's not worry about the CO2 which we are emitting. That's a fair approach. I'm not saying that it will be a problem. And I also told you, what if human civilization will get lost? Let's assume. Who cares? This is the entire universe. There might be many other civilizations. On this particular earth, plant kingdom will exist with more CO2. Why we should bother?
CO2 out of also. Okay. My question is, let's say a country like India, and we are focusing so much on limiting the carbon emissions. So if we, control that to a great extent, major efficiency, will our country get any benefit? Will our environments be clear, or it will be just, the global thing which, will affect our region as well?
Very good
So
question.
what is the incentive for our country to, invest so much into, this technology and then trying to, stop carbon emissions, fully knowing that it could be undone by our neighbors or some other countries? Thank you.
Very good question. See, when you are talking about CO2, it's a problem of entire world. It's not your problem or someone else's problem. Let me tell you, maybe in India it may not be true. But if the same question will be asked by someone else sitting in, say, Europe or in US, what solution you have? No solution. You cannot ask such questions. See, Europe and US, they produce, the entire product is being produced in China. And they're just buying from there. So whose problem is this? It's not their problem. Maybe in India we may say that no, we produce our own stuff. But those countries, can they ask this question? When you are importing your product from all over the world, is this your problem? No. It's not a problem. Everyone's problem. Everyone has to fix this. So the entire solar panel which we are getting, we are talking about this gigatons, gigawatts of where it comes from. They are emitting that CO2 for you, no? Can you really say that, okay, that CO2 will not count? That is also being counted. So we have to be very fair in this. They are, other countries are producing for you. They are emitting CO2 on your behalf. You will have to account for that also. We cannot say that I will not produce anything in this world. I will buy everything and I am CO2 free. This is what Europe is doing. But is that the right approach? No. You cannot do that. You cannot get away from all this. This is why I was trying to say that the only option for us is to basically reduce our need, which is not easy, I'm telling you. It's very difficult. It's very, very difficult.
That's going to be the subject of my lecture.
Certainly,
20
sir.
days later.
Great. I'll certainly attend that, sir. Yes, please, sir. Go ahead.
Thank you so much for the presentation, sir. I could see the technological aspects and improvements and R&D which put together for the carbon sequestration. So basically, I have a question, like we have some natural ways where sequestration happens, like with mangroves project or whatever the project, like with the existing nature-based solutions. So one difference is I see the scale where you talk about the amount of volume which is being generated. Apart from that, is that the other ways which we look into, apart from the scale of reducing the carbon, apart from that, what can be the difference between the existing situation, which is nature based, and this technological approach you are coming up with?
It's a very good question, sir. But as I was telling you, that all solutions has to be looked at. You have rightly pointed it out. Very recently, Udanidhi Stalin talked about 1,000 crore funding for mangroves and all. We are working with them. We are trying to identify locations where these mangroves will come up, how much CO2 will get sequestered and all those things. So it's not that we are not looking into it. So while we are delivering a solution to L&T, which is chemically capturing the CO2, how we are also delivering a solution to the government and other agencies which are trying to do it by natural ways. So that's what I was trying to tell you, that seagrass for that matter. Significant amount of funding from the government, state government, central government has gone into growing seagrasses. Okay, which captures significantly large amount of CO2. There is a program from last 10 years to do this. And we are working with all the Cambay Basin and all, we are talking about it. So these things are also ongoing. But as I was trying to tell you that everything would be required. Very pertinent point, and I agree with you that everything has to be done.
But if you mention nuclear energy, you are talking about fission energy. What about fusion? Fusion energy, like hydrogen, nitrogen. You know, you see.
Yes, sir. We are all aware of it. The technology is not there yet, so we will have to.
France has already built a fusion reactor.
Microsecond. Microsecond. It will take time, sir. When it happens, it will certainly be very useful. But right now, it's not the time to discuss that. Maybe 100 years away from today. Maybe 100 years, maybe too pessimistic, maybe 50, 60 years away from today. I think first we have to focus on whatever we have in our hand and how do we make it more sustainable. Future technologies will keep coming. That's not a problem.
Even disposal of a fission nuclear waste, that is also a challenge.
Really?
Yes, sir. If there is no further question, I think today, Women's Day, we should certainly take one question from her.
It's totally different. Mine is psychology, and your lecture was super. Being a housewife, for the future generation, our kids, what shall we have to do? What for emission of this carbon? It was somewhat apart from my knowledge, but what we have to say to our future? This is little bit.
I agree
Apart
with
from
you
our
completely, and I hope you understood everything which I told today, because I was trying to go to a level where everyone should be able to understand. Does not matter what was your background. For your kids, and I am telling you, I am also really. I have a son 8 years old, so all of us have to work together to solve this particular problem. We are trying to tackle it through technological point of view. For people, everyone else who are probably not helping out through the technology, we only one thing we try to always suggest that kids and all, they might be reminding you switch off the light, switch off the fan, and all those things. So all the basic sanitization we have to do. That is something which we'll have to always do. Anytime which we talk about, please try to be little bit more scientifically oriented so that we know exactly what is the science behind it. It will help you, it will help your kids also. Never believe that without science anything will move on. Science is very important.
Any plants or trees
Teach
that
science to your kids, they will do wonderful things.
okay, so any plants or trees that if we plant, we can reduce that.
Certainly, any number of tree you will plant, it will reduce CO2 emissions.
Specific any plants or trees?
I will tell you roughly the kind of weather we live in, tropical countries, roughly around 10 times 10 tons of CO2 gets captured, 10, maybe a little bit more, 10 to 12 tons of CO2 get captured per hectare of land, irrespective of what plant we are talking about. Mangroves have slightly other challenges because half of it is dipped in water and that emits methane, and all those challenges are also there. But regular planting of tree on land is not a big deal. You increase the number as much as possible. In fact, I'll tell you a very good news. In India, the forest cover has increased in last 5 years significantly. You will not believe that we have increased our forest cover significantly. There is still a lot of work which is ongoing, and it will improve our forest cover significantly because there is a huge thrust for this. And I'm sure over a period of time, this numbers of trees and all will certainly improve. And if we can help, that will be really nice.
Thank you, sir.
We'll take it offline.
Yes, sir. Yes, sir. Polymers are also being used to absorb carbon dioxide.
So can we?
I just answered half of his question, so don't worry about it.
No, I think, sir, this session can go on.
Yeah, I know.
The way you have involved yourself in the subject, not only as a professor.
I am only worried that everything is being recorded and it will go on YouTube. People will kill me, actually. That's the only thing I am worried about.
No, sir, I think the best takeaway was the last question by Madam.
Yes,
Said,
yes.
how can all of us contribute to this whole journey of CO2 by educating our children on some of these do's and don'ts?
Yes.
First of all, we have to practice it, then educate our children.
No doubt.
And as you rightly said, we are investing for the future.
Yes.
In fact, today, if there are some traffic jams, we are getting diverted because the whole metro trail project is for the future.
Yes.
After 5 years, somebody is going to benefit.
3-4 years, it will
so
be
that
much
is the
better.
way
Yeah.
we have to look at this as an investment rather than as a cost.
Yes.
There is a cost angle. I must really thank Professor for this awareness session. This is not a technical session.
Thank you, sir.
It's
Thank
an
you very
awareness. And really, thank you from the
Thank
bottom
you,
of
sir.
our
Thank
heart.
you.
And very section. Thank you. Mr. Chandramouli, sir.
Thank you. Thank you very much.
Oh, you are an alumnus. Thank you. Really nice to see you,
Former
sir.
research affairs secretary.
Oh, great.
It's my
8 years. I was
pleasant
elected
duty to thank
Oh, great.
Professor for this wonderful session. Many of us were very, scared that it might be very technical and what do we know about chemistry, but you have brought it to our level, and I'm sure this awareness will be spread. And I do wish that, we take this further to the schools and other, institutions so that the youngsters get to know of it.
In fact,
So-
next month I am here again to deliver this lecture from Popular Science series, actually, Popular
Okay.
Science lecture.
Right.
So hopefully there will be more young kids. That's
Young
what I
kids, yeah.
planned, actually. So
Yeah.
hopefully
We'll also try to organize it in another school sometime when at your convenience.
Sure, sure.
So thank you very much for attending this session, and let me just give you a few announcements for the future sessions. We have the next session on foreign policy, and this would be the former Secretary, Foreign Affairs Secretary, Mr. Vijay Gokhale, who's going to talk to us on India-China. And before that, we have one session, which is a youth outreach program. It is in the Etiraj College. So many of you who are interested can come. It is on 18th, and 18th is Kodanaiki. It's on a local, it should have been done today on Women's Day, but since we did not get the speakers, so it is basically on our own homegrown heroine, UV Kodanaigi, and Justice Prabha Sridevan will be speaking on that. This is on the 18th. On the 19th, we have Mr. Vijay Gokhale, Foreign Secretary, who's talking to us on India-China. And then at the end of the month, on 23rd, we have a session on economics. And this is by Professor Karthik Muralidharan, who is from, I think, Duke or one of these American universities. He's taken a sabbatical. He's written an exhaustive book on Indian economy. I'm sure many of you will be interested in that topic too. So you are welcome. So this is what CIC is all about. Last week we had one on Hindustani music. Today we are having it on chemistry. Tomorrow we are going to meet on social worker and also foreign policy. So this is what we do. We bring you various people from various walks of life. We are happy that you have encouraged us in our endeavors, and we hope to see you, more and more of you. Please spread the word around that we have this interesting platform where we discuss many of the issues which are pertaining to the common people. So please do attend our sessions in future too. Thank you.
Thank you for joining.